binary optimization, or QUBO in short. And so this is just a typical, this is just some kind of a mathematical formulation of our optimization problem. So we need to define our optimization problem as the problem of minimizing a polynomial of multiple binary variables of degree at most 2. So here you can see this binary variables that can be multiplied, but it can be at the degree 2 at most. And here we have some parameters, right? And now the question is to find the minimum, the assignment of the variables that would minimize the function that is defined. And why it is suitable for quantum computing, so in particular quantum annealing, because in statistical mechanics, in ferromagnetism, there is a famous model that is called the Ising model, which has, as you can see, has a similar form. So there are some variables, this time corresponding to spins, like spin up or spin down, which correspond to values +1 or -1, and there are some parameters corresponding to qubit biases and coupling strengths between qubits. And such a similar form, similar to QUBO, correspond to just Hamiltonian of a given quantum system. So it turns out that if we can define our optimization problem in terms of a QUBO, we can later encode it in a quantum hardware and then apply some quantum techniques like quantum annealing, for example, where first we start from a simple Hamiltonian and quantum system for which the Hamiltonian is, for which the ground state is easy to prepare. And then by slowly modifying the strength of the magnetic field, we should end up with a quantum system for which the Hamiltonian corresponds to the Ising model and the ground state corresponds to the solution of our problem. So in theory, it should be the global optimum, but in practice, it's difficult to achieve because, first of all, this evolution done by changing the strength of the magnetic field should be done very slow, and there are even some formulas explaining how slow it should be done. And in addition, this evolution should be adiabatic to ensure that we stay in the global optimum. In practice, it's difficult to ensure that we have the adiabatic evolution. But instead, even if we do not find the global optimum to our problem, there are still some chances that we'll find heuristically optimal or suboptimal solution to our optimization problem, which can be still quite good. So we can consider this kind of algorithm, like quantum annealing, as another approximation or another heuristic algorithm, let's say. And now how to do it in practice, so how to transform our optimization problems to the form of QUBO. So first I will give a brief example that is inspired by the paper published by researchers from Volkswagen and D-Wave. So D-Wave is a company from Canada developing this quantum annealing machines. There are some controversies around it, but at least there's already also several publications demonstrating how some computations can be done using these quantum annealing machines. So what they did, so they also wanted to solve the problem of routing multiple vehicles. So the paper is titled Traffic Flow Optimization using a Quantum Annealer. So first they built a road network. So the road network was just a realistic road network in Beijing, in China. And they had some number of vehicles corresponding to taxis traveling from the city center to the airport. And they had information about the real routes taken by the taxis. This data were from just GPS data, by just tracing the trajectories of the taxis. The data set was called T-Drive. And then for each car, they just added 2 alternative routes between the same source and the same destination. And of course, it was assumed that the cars may share road segments. And of course, the more cars we have on a given road segment, the longer is the travel time, or the lower is the average speed of these cars. And it was assumed that the travel time is proportional to the square of a number of cars on a given route, which is a simplification, but it's not that far from the truth. So there are some ranges of the traffic density in which it's quite accurate. And thanks to this simplification, they were able to just encode this problem the form of a QUBO and then solve it using a quantum annealing machine. And of course, the goal was to minimize the total travel time of all the cars. So how they did it? So they introduced some binary variables corresponding to the information whether the car I takes the route J. So just to recall, each car has 3 potential routes to take. So of course, then we need to add some constraints, like we want every car to select exactly one route, 1 out of 3. So this constraint should be satisfied for all cars. And then when we calculate the cost, then the cost of the total travel time of all cars traveling through a road segment S is, and it was assumed that it's proportional to the square of the number of cars traveling through this route. So it's proportional to, or it's equal to the square of the all the cars traveling to a given road segment. So then if you want to calculate the total travel time on the whole road network, then this is the total cost. And in theory, it could be just our objective, our optimization problem, for our optimization problem. But it's easily, you can easily see that the minimum, the minimum for this function is just assigning value 0 to all variables. But it's not something interesting for us because we want every car to select exactly one route. So we need to add some additional constraints, ensuring that this condition is satisfied for all vehicles, right? So so first, this part was this unconstrained binary optimization part, but we had these additional constraints, and these constraints can be easily added to our objective function to just keep this quantum unconstrained binary representation. And how to do it? We can just add the sum of all these terms that should be equal to 0. And if any of this condition is not satisfied, then this square is greater than 0. And if we set the value of a parameter to be large enough, then this part can become significant. So any solver exploring the space of possible options, possible assignments of these binary variables, would not consider this or such assignments for which this part is very high. Right? So we would like to minimize everything, so we minimize the total cost, but at the same time keep this part equal to 0. And it can be just ensured when the value of this lambda parameter is high enough. So this is what they did. And this is still the form of quadratic unconstrained binary optimization. So it was encoded on D-Wave's quantum annealer, then they performed some computations. The experiment was run for 418 cars. There were 3 times more logical variables, so the space of possible solutions was astronomical, and in such a large space, they wanted to find the global optimum. So I'm not sure if they really found the global optimum, but it seems that they managed to find a solution that was better than in the original traffic that happened in Beijing, when every car just behaved in such a way that in uncoordinated way, right? So every driver wanted to just select the shortest route, but in theory it led to higher traffic density in some areas. The computations took about 22 seconds. In the paper, there was no comparison with any classical algorithm, so we cannot say that classical algorithms are not able to solve it better or faster. I'm quite certain that some classical algorithms should be able to do it at least equally well, but at least it was a demonstration that this quantum annealing machine is already able to run some meaningful experiments and obtain some meaningful results for a real-world problem. Okay, and it was an inspiration for my research group, and we started thinking about applying similar approaches to solving optimization problem in logistics, but this time we wanted to focus on anti-hard problems like the travel and salesman problem. So in our vehicle routing problem. So in general, in these problems, we have a directed graph with non-negative cost assigned to edges. And in the TSP problem, we have unselected vertices in the graph. So you can think about them as our customers. And so we can think about ourselves as an e-commerce company willing to deliver some products to our customers. And the question is, what is the shortest possible route that visits all of these customers, and returns to the original vertex, that is our depot. And in the original traveling salesman problem, we have only one vehicle, but there is an extension or generalization of TSP that is called vehicle routing problem, in which we also have n-selected vertices in our graph, and these are our customers. And we answer a similar question, but this time we can assume that we can return to the depot earlier, or we can also assume that we have more than one vehicle. So we have a fleet of vehicles, up to n vehicles that can serve all our customers. Or there can be just a single vehicle but returning to the depot and taking some new products. And there are also some other even more realistic and more complex variants with some additional constraints, like capacitated vehicle routing problem with bounded capacities of vehicles. And there are also variants with time windows. So then we assume that the customers can be served only in some particular time windows. And there are many, many other even more realistic variants. And it's not difficult to prove that all these problems are NP-hard, assuming that we know that the traveling salesman problem is already NP-hard. So it's likely that there's no polynomial algorithm able to solve this kind of problems. So find the optimal, globally optimal solution for these problems for very large instances. So the state of the art is rather using heuristics, meta-heuristics, so algorithms aiming to find approximate solutions. So in this talk, I will demonstrate how we can tackle this kind of problems using quantum annealing and potentially some other quantum algorithms that we have already started exploring. So first, we need to introduce this specific notation. So let's assume that we have a set of our vehicles. So we have up to n trucks or vehicles. We have n+1 nodes in our graph, but the nodes from 1 to n are our customers, and n+1 is our depot. And then for each edge in our graph, we have a cost of traveling from node I to node j. And we can assume that cost of staying in the same location is equal to 0, which is not always true, but this is some simplification for these particular variants. And then we introduce the binary variables with 3 indices, I, j, k. And we can assume that these binary variables, for which we would like to find the optimal assignments, should be equal to 1 if in a given setting, in a given solution, the vehicle I visits the node j as the key location on its route, and otherwise it is 0. So as you can imagine, in some feasible, for some feasible solutions for which we have some particular routes, most of these variables would be equal to 0. But some should be equal to 1, of course. So I is from the set T, the set of vehicles, j is from the set of nodes, and I is also from the set from 0 to n+1. And first, some observations. So the first observation is that for each vehicle, x, I, n+1, 0 should be equal to 1, which means that the depot is always the initial location, right? And there cannot be any other node, any other customer visited at the time 0 as the first one. So we always start from the depot. And here another assumption or observation is that the depot should be always the last location on each route, and each car stays in the depot after reaching it. And this condition just tells it, right? So if we achieve the depot at some point, then for all larger indices, for the next time steps, we stay in the depot and we cannot visit any other node. So these are just some technicalities. And this is maybe a bit complex QUBO formulation for our objective function. So the first, I will not go into much details here because it's, as you can see, there are so many indices, but I just wanted to give an intuition how to interpret it. So this first component in the sum is a sum of all the cost of travels from the depot, from the starting point, to the first visited node. So this is just the first section of each car's route. The second component is a cost of the last section of a route, so from the last visited customer to the depot, but in a single special case when a single car serves all n orders, all n customers. And only in such a case this component can be greater than 0. And the last part is the cost of all other sections of route. So actually this is, let's say, the main part. So we have the cost, and this is non-zero only if this specific edge is really covered in our solution, right? That one of the vehicles, the vehicle M, travels from customer I to customer J between time steps n and plus 1, right? So then this is equal to 1, and then we add the cost to the total cost. And these two first components are just to handle some special corner cases. Okay, but we also have to introduce some constraints. So in order to do it, let's consider such a relatively simple binary function where these binary variables are from the set 0, 1, and we can observe that the minimum value of this function is equal to -1, and this can be achieved only if exactly one of these binary variables is equal to 1, right? So this is the minimum. Okay, and in order to assure that each deliverer, each customer is served by exactly one vehicle and exactly once, we have to consider this constraint. So this sum should be equal to 0, and this is equal to 0 if and only if each delivery, each customer is served by exactly one vehicle and exactly once. So this is only then this part is equal to 0. And the second part, the second component, is equal to 0 if and only if each vehicle is in exactly one place at a given time. So if we want to ensure that these conditions are satisfied, we should ensure that this total sum is equal to 0. So we call it Q. So similarly as in the approach introduced by researchers from Volkswagen and D-Wave, we have to add this constraint and set the value of the parameter in front of this, let's say, part or component corresponding to the constraints to ensure that when our solvers look for optimal solutions, this part should be just always equal to 0. That if it's not equal to 0, then this component should start dominating, and the total solution should not be considered as the optimal solution by the solver. So in total, this is our final QUBO formulation. So as you can see, this component, thanks to this approach, this is also QUBO formulation, so quadratic unconstrained binary optimization. So this was the first approach. Then we slightly improved this approach, and we introduced this solver was called the full QUBO solver, or to be precise, this QUBO formulation was called full QUBO solver. And later we introduced the average partitioning solver. Because in such formulation, as you can imagine, the number of binary variables is quite high, and as you probably can expect, these binary variables should correspond to our logical qubits. So we would like to minimize the number of qubits, because otherwise we will not be able to solve large instances of our problem. So in order to decrease the number of variables for each vehicle, we can assume that every vehicle serves approximately the same number of customers, up to A plus L deliveries, where A is the total number of customers divided by the number of vehicles, and L is just a parameter which controls the number of orders. So this is quite realistic, because in practice, when we have a fleet of vehicles, we would like all these vehicles to be more or less evenly loaded, right? So this is quite realistic. So then the number of variables is lower, which simplifies computations. Then we introduced another solver that we called dB-scan solver. So this is already a hybrid approach, in which we first perform a clustering of our graph using some classical algorithms like dB-scan. And then for all these clusters, we solve an instance of TSP for all the nodes in a given cluster separately. And this instance of TSP can be already solved using, for example, the full QUBO solver or average partitioning solver that I've discussed. So then if the number of clusters is equal to or lower than the number of vehicles, then the answer is no immediately. Otherwise, the solver runs recursively considering clusters as deliveries, so that each cluster contains orders or customers, which in the final result are served by one after another without leaving the given cluster. We can also conclude that by limiting the total sum of weights in a given cluster, this algorithm can solve this capacitated variant of vehicle routing problem, right? If all capacities of vehicles are equal. So this is already this more complex, more realistic variant. And finally, we introduced another algorithm. So in this deep distance solver, we first applied classical clustering and then performed quantum algorithm for to solve TSP. But in solution partitioning solver, this approach is reversed. So first we solve the TSP problem on the whole large graph, and then divide the solution into clusters and assume that in each cluster, the customers are served by just a single vehicle. So first we have the solution, and then we try to find the optimal division for the clusters using dynamic programming. Right, so this is the formula for this dynamic programming. So here, this D, P, J, S correspond to the cost of the best solution of orders from D1 to DI in this case. So these are our customers, and for the given set of vehicles. So here we just consider that we have the set without a single vehicle, and then this is the cost for assuming.
Strange.
Okay, let's wait. It's coming. Need some connection. Okay, I cannot see here, but I can see there, so I can try to continue, but I'm not sure if our colleagues on Zoom can hear us.
Actually, it seems that one of the projectors is gone, or because I think the projector, there is a button for a projector. Anyway, please continue, because this screen is still, look, on that side.
Yes.
It's still visible. So.
All right, I can also say that. Yeah, so this is just a formula for dynamic programming where we just add more and more vehicles. We add next vehicles in an iterative way and construct the solution for the larger set of vehicles by analyzing the solutions for smaller number of vehicles and also smaller set of customers. So this is just a classical approach. We can also speed it up a bit but by assuming that instead of considering sets of vehicles, we can consider a sequence of vehicles and assume that we attach them to the levers in such an order, because actually if the vehicles are identical, they have the same capacity, it really is not important what is the sequence of considering vehicles in this case. So then this dynamic programming formula is even faster, and the computations are even faster as well. And for most of the benchmarks that are available on the internet, it is also assumed that the capacity of the vehicles is just constant in the whole fleet of vehicles. So this is a reasonable assumption. So now let's go to the experiments. First, the setup of experiments. So our goal was to compare the results of different algorithms, both quantum, hybrid, and classical algorithms, on several data sets. And for quantum hybrid algorithms, we run experiments using D-Wave's deep platform, so using this quantum annealing approach, using a QUBO solver provided by D-Wave, and we perform computations on quantum processing unit and on CPU. So on CPU, it was just a simulation of the quantum annealing process. And there was also a hybrid solver provided by D-Wave that performed computations on quantum processing unit and classical processing unit at the same time. So in case of classical algorithms, we tested some meta-heuristics like simulated annealing, the algorithm evolutionary annealing, and dB simulated annealing. And we ran experiments, we conducted experiments on two data sets. So one was a standard benchmark data set that is very popular for capacitated vehicle routing problems called Christofides data set. Another data set was built based on a realistic road network of Belgium, close to Brussels, and it was acquired from the OpenStreetMap service. Why Belgium and not Poland, for example? So this research was carried out in a project funded by the European Union, in which one of our partners was a Colorway company. It's a company, it's a retail company from Belgium, and they were interested in introducing last mile delivery of their products from their magazine to the customers in Brussels. So that's why we consider this sub-network of the original realistic road network of Belgium. But the dataset was acquired from the OpenStreetMap service, which has quite accurate representation of the global road network, not only here in Europe. A bit more about the dataset. So this Christophided dataset is, as I said, is a standard benchmark dataset. Many research work compare the results on instances from this dataset, and you can see the number of vehicles and the capacity of the vehicles and number of orders in different for different instances that we've considered. Regarding this more realistic dataset built by us based on OpenStreetMap data, there were different sizes of the instances, starting from just several orders to even hundreds of orders as well. Okay, so maybe I'll not go into details regarding all the results of experiments, but just wanted to tell you that we started from this first solver that I introduced, and it turned out that we already struggled to solve these problems using quantum processing units. So that's why we started running it. So even for small instances and for a small number of vehicles. And one of the reasons is also the number of binary variables that we have in these formulations. So in general, the number of qubits that we need is more or less proportional to the square of the number of customers times the number of vehicles that we have. So you can estimate the number of qubits that is necessary. So that's why we in later experiments we rather focused on hybrid and classical simulations of the quantum annealing. But even the first experiments on medium data sets prove that this full QUBO solver is just not able to solve even some relatively small instances, while 3 other solvers that we've introduced were able to solve them at least. So the solutions were not only good, not always good, but at least we were able to get some solutions. For the biggest instances from this data set prepared by us, it turned out that the last 2 solvers that we introduced are the best, and it already seemed that the solution partitioning solver is the best one. And later we started comparing the solution partitioning solver with some classical algorithms. So first we did it on the datasets that we created using OpenStreetMap, and the results were usually worse than for classical algorithms. But in some cases, for some instances, our quantum algorithm or hybrid algorithm in this case was able to outperform some classical algorithms, but it never outperformed all of them. And it was the same for experiments on the Christophided dataset. So usually for most of the instances, this hybrid algorithm was better than standard simulated annealing or even B algorithm, but it was usually worse than evolutionary algorithm and DB-scan solver with simulated annealing. But so this last algorithm was usually the best, but in some cases it was not able to find feasible solutions. So it turned out that this hybrid solver is, let's say, average. So it has comparable performance to some quite good classical algorithms that are available in the literature. So it was quite promising, and this was one of the reasons why we also wanted to continue this work and these experiments. But first, some conclusions. So first of all, it doesn't make sense, or at least several years ago when we ran these experiments, it didn't make sense to run experiments on quantum processing unit, only on QPU for large test cases. So we had to run either class simulation of quantum annealing or a hybrid solver for this. We compared the solution partitioning solver, so the best hybrid solver that we've introduced, with some classical meta-heuristics, and it usually gives a bit worse, but sometimes better results. So, but we can say that it's comparable or maybe a bit worse than the best classical algorithms. The code is publicly available. If someone is interested, it's possible to check it and give it a try and run it for some other instances. And now about some other research directions that we've actually already started some time ago. So these QUBO formulations that we've introduced can be also tackled not only using quantum annealing, but also using gate-based quantum hardware and variation quantum algorithms like VQE, QAOA, and their variants like recursive QAOA, layered VQE, filtered VQE. So these are just examples of these variation quantum algorithms that we've tested. But they were able to run, to give us meaningful results for very, very small instances with up to 10 customers and maybe 1, 2, or up to 3 vehicles. So these are still not interesting instances for us, at least for quantum hardware, because we can potentially simulate these algorithms on classical hardware as well. We also started working on scalability, right? Because we can see that this is one of the problems. We are not able to solve very large instances using quantum hardware. So we started thinking about some kind of graph clustering or graph clustering techniques, which could first make some smaller instances. Then we could run our quantum algorithms on the smaller instances, and then combine them, the solutions, to build the solution for the larger graph again. So it's a similar approach to divide and conquer. And of course, it's interesting to investigate for which scenarios these hybrid algorithms give the best results comparing to classical algorithms, because we have observed that for some scenarios, our quantum or hybrid solver managed to outperform at least some classical algorithms. Not all of them, but at least some of them. And the results were comparable. So definitely, this performance depends on the type of a given instance, like the topology of a graph, or maybe also relation between the number of vehicles and the number of customers, and so on. And it's also good to start thinking about more complex, more realistic variants like capacitated vehicle routing problem with time windows. There are already papers showing how to do it by introducing some additional slack variables, but it will require some additional qubits as well. So perhaps we can do it better. So we've also started thinking about some other way of encoding the data and then encoding the variables to just reduce the number of qubits that we will need. Finally, we can try to apply some other QUBO formulations. I've presented just one approach, but we are also aware of some other QUBO formulations for this kind of problems. And as you saw, for this kind of QUBO formulations, there's always this relaxation parameter that controls the trade-off between the quality of the solution and probability of achieving a feasible solution, satisfying all the constraints. So we can also try to play with the values of this hyperparameter, and we can even try to apply some machine learning techniques, or classical machine learning techniques, to find good values of this relaxation parameter. And there are already some papers showing how to do it. With this, I would like to thank the contributors of this research work, because there were many people contributing here. And as I said, it was already published, and this research was initiated within the research project carried out and support the University of Warsaw, supported by the EIT Food. But it was already a few years ago, and since that time, I've started working on this project within the QIntern program of the QWorld organization that I'm currently coordinating. So I would like to thank you for your attention, and if there are any questions, I will be happy to answer.
All right. Great, thanks for your talk. So do we have any questions to the speaker? Maybe I will come, so microphone is always better.
I have some question about the results table that you showed, that which are the units, because at the beginning I said that probably it's seconds, but one of the next things are really small units. These are seconds, or it's unit units?
Yes. To be honest, I don't remember. So there were some costs introduced, but they should correspond to the time, but I'm not sure if they were just seconds.
So more, the better.
The lower, the better. Yes, the lower, the better. Mm-hmm.
And in regards to that, have you checked which is the region in which this hybrid method works? In the sense of, if this method have a really good convergence with small samples, if it's really good in the divide and conquer domain, which the region or the size of the problem that this hybrid method could outperform the normal algorithms.
Mm-hmm. So it's hard to say because it seems that when we compare these methods with classical algorithms, it seems that so of course there are some limitations in case of quantum algorithms due to the number of qubits that we need, right? But up to this limit, up to this limit, it's really hard to say. So for sure it depends not only on the number of qubits or the number of customers, but also on some other factors like the topology of the graph. But actually, we haven't studied it yet. So this is one of these research directions that I've put here to investigate for which scenarios these hybrid quantum algorithms give the best results compared to classical algorithms. So we haven't performed such an analysis yet.
Thank you very much.
Thanks.
Thank you. So do we have any more questions in regards to the presentation?
A very basic question, but what is the what are main differences between quantum annealing algorithms and classical annealing algorithms? Except using bits and qubits, something completely systematic.
All right. It seems that I cannot move my slides now for some reason, but because I had some additional slides. So so I would say that this quantum annealing approach is inspired by, let's say, classical annealing, but you know, in the simulated annealing, we just locally explore our space of options, of solutions, and we just decrease the temperature, which also decreases the probability of just jumping to some other solutions, right? So this probability changes it in time. So this is a simulated annealing. But in case of quantum annealing, as I described at the beginning, or maybe now, no, it doesn't work. Okay, so in this quantum annealing, we have this QUBO formulation for our problem that is encoded in a real quantum hardware thanks to correspondence with this Ising model, basically, right? And then we first let's say this our objective function corresponds to the function of the energy of our quantum system, right? And when we change the strength of a magnetic field, we also change our quantum system in particular, and we also change the global optimum of the current problem, and so we change the landscape of the function that we optimize, basically, right? So at the end, we should achieve the final function corresponding to our optimization problem. And during this process, in theory, there should be also something there is also something like quantum tunneling that can allow this process to, let's say, jump from one or the previous global optimum or the current solution to some other solution for which the energy is potentially lower. And this energy also corresponds to the solution for our problem. So there are some similarities because in one case, in case of simulated annealing, we change the, let's say, this abstract temperature, which controls the probability of just jumping to some other regions of the space of solutions that we explore. In case of quantum annealing, in time we just go closer and closer to our objective function that we want to optimize, let's say. And we change the strength of a magnetic field in practice. So at least this is how I understand how it works, but I'm not sure how exactly this D-Wave company implemented in their machine, because there are also some controversies regarding the work of these quantum annealing machines from D-Wave.
So essentially, the difference between classical and quantum annealing is that classical annealing finds local minima of potential, but you cannot come across certain paths. But in a quantum annealing, you have also effect of quantum tunneling, which speeds up. That's the main difference. Yeah, any more questions in regard to the presentation? Okay, if not, let us thank the speaker again. Okay.